Marhaba. In this session, we want to continue learning new methods for constructing new propositions from older propositions. Remember, previously we defined what is a proposition. It's a declarative statement which is either true or false, but not both. So it's a statement which declares an opinion and it has a truth value. It's either true or false. Okay, and then we learned before that we use letters such as P, Q to represent such statements, such propositions. And then we said if we start with two propositions, say P and Q, then we can define new propositions, and we learned three methods or four. We learned how to define not P, the negation of P, or the conjunction of P and Q, or the disjunction P or Q, and we also learned the exclusive or P, exclusive or Q. And we said that all these new statements are also propositions because we defined its truth value based on the truth value of P and Q. So remember, for example, P and Q will be true only in one case, when P is true and Q is true. Otherwise, its value is false, truth value is false. Now we want to learn other methods of building new propositions, and the first method, it's called the conditional statement. So let me define what is the conditional statement. Suppose P and Q are propositional variables or are propositions, then the conditional statement we read it as P implies Q, and we write it as P arrow Q is the proposition is the proposition if P then Q. Okay, so again, we start with two propositions, P and Q. We build a new one, which is P arrow Q, and it stands for if P then Q. Now we need to define, for this new proposition, we need to define a truth value. Now it is false, so P implies Q, this conditional statement is false only in one case, only when P is true and Q is false. Okay, so this whole statement, new statement, we will declare its value to be false when P is true and Q is false. Otherwise, in the three other cases, it will be a true statement. Okay, let me say that P in a conditional statement of this form, P implies Q, we call P the hypothesis of the statement, hypothesis, or the premise, okay, and we call Q the conclusion. Okay, so this means that a conditional statement P implies Q is false only when the hypothesis is true while the conclusion is false. Okay, note that the statement P implies Q asserts that Q holds on the condition that P holds. Okay. That's why we call it a conditional statement. So we know that the conclusion holds given that, or based on the condition that the hypothesis P holds. Okay, let's draw now I think you should be able to construct the truth table. So here is P, here is Q, and here is the new proposition P implies Q. Again, we have four scenarios here, T, F, F, and here we have T, F, T, F. So we said there's only one case where P implies Q is false, when we have true hypothesis and false conclusion. It's the second row. So in this case, P implies Q is false. Otherwise, P implies Q is true. This is how we defined it. Okay, let me say a few comments about this. So now, suppose you know that the whole statement is true. So the conditional statement is true and the hypothesis is true. So this leads us to the first row. So here we have P implies Q is true and the hypothesis is true. So and in this case, see that the conclusion is true. So what I am saying that if you know that the hypothesis is true and the conditional statement is true, then the conclusion must be true. Now, if you know that the conditional statement is true, but the hypothesis is false, then the conclusion can be true or false. It doesn't matter. Look, I'm talking about these two cases. The third and fourth row. In these two cases, we have true conditional statement. See, the conditional statement P implies Q is true and the hypothesis is false. However, in the third row, the conclusion is true. However, while the conclusion in the fourth row is false. So I'm saying that if you have a true conditional statement with a false hypothesis, then you know nothing about the conclusion. It could be true or false. Okay, the only time where you can be sure that the conclusion is true is when you have a true conditional statement and with a true hypothesis. Okay, and the only way where the conditional statement is false is in this second row, which says if you have a true hypothesis and a false conclusion, then your conditional statement is false. Okay. Now let me say how do we read P implies Q. So P arrow Q can be read in several ways. The first way is if P then Q. The second way is P implies Q. So there are many ways to read P arrow Q or the conditional statement. P implies Q. And third, you can say Q, the conclusion, follows from the hypothesis P. And what else? We say that P, the hypothesis, is a sufficient condition for Q. Is sufficient for Q. And we also say for P implies Q that Q, the conclusion, is necessary for P, is a necessary condition for P. Is necessary for P. Okay. Now let's have examples. So all of when you see this, you can read it in any way you want. You can say if P then Q, or you can say Q follows from P, or P is sufficient for Q, or you can say Q is necessary for P, and so on. Okay, let's have some examples of conditional statements. For example, okay, let's look at this conditional statement. If water molecules exists, if water molecules exist, then oxygen atoms exist. Then oxygen atoms exist. Okay. Now this is a conditional statement because it's of the form if P then Q. Now what is the hypothesis of this conditional statement? This is the hypothesis. This is P. Water molecules exist. What is the conclusion? It is oxygen atom exists. This is P and this is Q and this is a statement of the form P implies Q. Now you ask yourself whether this is true or false. Okay, in the world it is true because water molecules is made from 2 hydrogen atoms and 1 oxygen atom. So whenever you have water molecules, you will have oxygen atoms. Okay, another example is if Layla learns mathematics, then Layla finds a job. Then Layla finds a job, and here again this is a conditional statement. Here is the hypothesis, Layla learns math, and here is the conclusion, Layla finds a job. And now this statement could be true or false. When could it be true? It could be true, the whole thing could, so say this is P implies Q. This whole statement could be true if Layla didn't learn math, because if Layla didn't learn math, then we have a false hypothesis. And see here in the truth table that when we have false hypothesis, look, we have true conditional statements. Okay, so the first case where this conditional statement is true is if the hypothesis is false. Okay, now suppose Layla learns math. She did learn math. Then if she found a job, then this will be true. If she didn't, then this is the only situation where a conditional statement is false. Again, when a conditional statement is false is when the hypothesis is true while the conclusion is false. So that this conditional statement is false if Layla learns math and she did not find a job. Then this statement is false. Okay, what else we have? Here's another example. If there is rain, okay, if there is rain, there are clouds. There are clouds, and again the hypothesis is there is rain, the conclusion there are clouds. Okay, then there are clouds. Okay, you can have also if there are clouds, then there is rain. If there are clouds, then there is rain. Okay, so in this conditional statement, there are clouds is the hypothesis, and what is the conclusion? There is rain. Okay, we usually end our statements with full stops. Okay, now you think which one is true, which one is false, or when one is true and when the other is false. Okay, now let's have another example of a conditional statement having processors is necessary for manufacturing computers. Okay, see what is the form of this statement. This is a conditional statement. What is the hypothesis and what is the conclusion? So here you need to see that this is the conclusion. Processors is the conclusion, and having manufacturing computers is the hypothesis. Okay, see, this means that if you have computers, like having or manufacturing computers implies that we have processors. This is the meaning of this statement. If we manufacture computers, then we have processors. Or another way to see it is to say that processors are necessary for computers, or computers are sufficient for processors. Okay, so these are different examples of conditional statements. Again, we write a conditional statement as P arrow Q. We call P the hypothesis or the premise, and we call Q the conclusion. Okay, now if we are given a conditional statement, then we can form other related conditional statements. The first one is called the contrapositive. Okay, the contrapositive of a conditional statement P implies Q is not Q implies not P. Okay, again, so the contrapositive of P implies Q is the statement which is the negation of the conclusion implying the negation of the hypothesis. This is, as you see, it's another conditional statement. It says if not Q, then not P. Okay, the second conditional statement is the converse. Okay, the converse of P implies Q. So suppose you are given a conditional statement P implies Q, and I ask you what is the converse. The converse is Q implies P. So this is a new conditional statement whose hypothesis is the conclusion of the original one and whose conclusion is the hypothesis of the original. Okay, see here, this is a conditional statement. Its conclusion is P, but P is the hypothesis of the original. Okay, and finally 3, the inverse of P implies Q. The inverse of P implies Q is not P implying not Q. Okay, this is the inverse. So it is the negation of the hypothesis implying the negation of the conclusion. Let's have a quick example. Okay, suppose we are given a conditional statement which is the following one: if there is electricity, then there is light. Then there is light. Okay, so this is a conditional statement of the form P implies Q. What is P? What is the hypothesis? There is electricity. What is the conclusion? There is light. Okay, now what is the contrapositive of this statement? The contrapositive is if there is no light, there is no electricity. And what is the converse? If there is light, there is electricity. And the inverse is if there is no electricity, there is no light. Okay, shall I write them? Okay, contrapositive. Let me just write the contrapositive. How do we compute the contrapositive? It is the negation of the conclusion. So okay, maybe we should, this is easier. This is the hypothesis, and this is the conclusion of the given conditional statement. To compute the contrapositive, you negate the conclusion. So if there is no light, then the negation of the hypothesis, then there is no electricity. Then there is no electricity. Okay, I'm not asking if this is true or false. I'm just saying you are given a conditional statement and you are asked to compute the contrapositive, the converse, and the inverse of the given conditional statement. Okay, and now so up to here, what methods we learned to compute a new propositional statements? We have the negation, we have the conjunction, disjunction, and now we learn the implication or the conditional statement. Just forget about the exclusive or now. Okay, now we want to learn about the biconditional statement. By the way, all of these symbols, we call them logical operators. Logical operators or logical connectives. Okay, now the next operator, logical operator, is the biconditional statement. So let us say what is the biconditional statement. Okay, suppose P double arrow Q. Okay, so we are given two propositions P and Q, and then we form a new proposition called the biconditional statement. We write it in this way, P double arrow Q. So what is this? Is the proposition P if and only if Q. Okay, so we start with two propositions P and Q. We form a new proposition called P if and only if Q, or we call it the biconditional statement. And now it remains to define its truth value. So this new statement, P if and only if Q, is true only when both P and Q have the same truth value. Either both are true or both are false. Only when both P and Q have the same truth value. Same truth value. Okay, so what does this mean? Let's construct its truth table. So here we have P, we have Q, and here we have then biconditional statement P if and only if Q. Now again we have four scenarios for two propositional variables. Okay, again it is true only when both have the same value. So here in the first row both are true, so it's true. In the last row both are false, so again because they have the same truth value it is true. In the second row they have, and third row they have different truth values P and Q. So here P if and only if Q is false. Okay, so we want this new statement to be true only in two cases, when both are true or both are false. Otherwise, when one is true and the other is false, we declare it to be false. Okay, there are several ways again to read this new proposition. So for example, the first way is P if and only if Q, and second we can say P is sufficient and necessary, and necessary for Q. Okay, and we can also say P is equivalent to Q. Equivalent because it is true only when they have the same truth value. Okay, another way is to write P and then I double F. I double F, it's a shorthand for if and only if. So P if and only if Q. Okay, so here are the different ways to read this new proposition. So now we are ready to say what is a compound proposition. So a compound proposition, which is the title of this session, okay, is any proposition you construct by doing the following. One, start with propositional variables, say P, Q, R, S, T, any propositional variables you want. Remember, a propositional variable, it's a variable which represents a proposition, and a proposition, it's a declarative statement which is either true or false, but not both. So start with any variables you want, and second, repeatedly apply the logical connectives we learned, which are the negation, the conjunction, disjunction, implication, and the if and only if, or the biconditional operator. Okay, forget about the exclusive or in the construction of compound propositions. So let's have an example. So P itself, P is a proposition or compound proposition. By the way, from now on I will not differentiate between proposition or compound proposition. So P is a proposition now, and Q as well. Now P and Q is a proposition. Now P implies Q is a proposition, P if and only if Q is a proposition, R implies S is a proposition. Now look, this is a proposition and this is a proposition, so we can connect them with any operator, with any of these operators. So we can say P implies Q and R implies S. So this is a new proposition. See, this whole thing is a new statement. It says if P then Q and if R then S. Okay, what else we can have? We can have, for example, P or S, and now we have, so now this is a proposition and this is a proposition. So now we can apply the logical connectives on these propositions. So I can apply the negation on this one, so we get not P if and only if Q. So this is now a proposition. I can connect this and this with implies. So this, if you want, like this implies P or S. Okay, so how do you read this proposition? If now we have a conditional statement. You see, the whole thing is a conditional statement. What is the hypothesis of this conditional statement? It is this thing, this proposition. This is the hypothesis and this is the conclusion. So how do we read this conditional statement? We say if not P, if and only if Q, then P or S. Okay, and see, we can construct propositions as long as you want, and we have infinitely many propositions. So, for example, we have this P and P or S, or S if and only if T. So now this is a disjunction of these two, and now we can take this as a proposition and take it conjunction with the negation of P. Okay, so now we have a longer proposition. Okay, so again, a compound proposition, you start with the propositional variables and then you apply the logical operators to construct more and more compound propositions.